You already know bubble sort, O of n squared, lots of tiny swaps. In this lesson I will show you a different algorithm. Same runtime, same problem, completely different strategy. It is called selection sort. And it matters for one specific reason: selection sort almost never swaps. When writing to memory is expensive, this is the sort you reach for. Here is the plan. The one idea behind selection sort: 8 lines of Python. One example walked step by step. How it differs from bubble sort: comparisons the same, swaps very different. When you should actually use it. Here is the whole idea in one sentence. Find the smallest element in the unsorted part of the list. Put it at the start of that part. Then do it again, ignoring the first position. Then again. After k passes, the first k positions hold the k smallest values in sorted order. After n-1 passes, the whole list is sorted. The trick: think of the list as 2 regions. On the left, the sorted region grows by 1 each pass. On the right, the unsorted region shrinks by 1 each pass. Every pass, you scan the unsorted region end to end, find its minimum and swap that minimum into the boundary position. One full scan of the unsorted region, the scan is the cost. The swap is almost free. Why is it still O of n squared? n-1 passes, 1 per element that needs placing. Each pass scans the entire unsorted region to find the minimum. That is n-1 comparisons the first pass, n-2 the next, and so on down to 1. The sum is n times n-1 over 2, quadratic in n. Same growth as bubble sort. Selection sort in 8 lines of Python. Define a function that takes a list. Outer loop, for I from 0 up to n. Start by assuming the current position holds the minimum. Track its index in a variable min_ix. Inner loop, for j from I plus 1 up to n. If r at j is smaller than r at min_ix, update min_ix to j. After the inner loop finishes, swap r at I with r at min_ix. Return the sorted list. Same list as bubble sort 52814, so you can compare directly. Pass 1. Scan the whole list. Smallest is 1 at index 3. Swap it with index 0. List is now 12854. Pass 2. Scan from index 1. Smallest is 2 already at index 1. No swap needed. List unchanged. Pass 3. Scan from index 2. Smallest is 4 at index 4. Swap with index 2. List 1, 2, 4, 5, 8. Pass 4. Scan from index 3. Smallest is 5 already in place. No swap. Done. 10 comparisons. Only 2 swaps compared to bubble sort's 4 swaps on the same input. So why does selection sort exist if bubble sort runs in the same time? Count swaps, not comparisons. Bubble sort makes up to n squared over 2 swaps in the worst case. Many small fix-ups. Selection sort makes at most n-1 swaps, 1 decisive swap per pass. When matters, when writing to memory is expensive. Sorting records where each row is 10 kilobytes. Flash memory where writes wear out the chip. In most situations it does not matter, and you would reach for a better algorithm. But there is exactly one niche where selection sort is right. So when do you actually use it? Almost never in regular application code. But it is still worth knowing because it teaches the pattern of maintaining an invariant. The sorted prefix grows by 1 each pass. You will see that pattern again in insertion sort and in every dynamic programming algorithm. It is also a clearer teaching example for how do you count operations. Swaps and comparisons are obviously different here, and it is a common interview question. You now have 3 sorting algorithms: bubble and selection, and the quick sort we will cover next. You know why selection sort exists, how it differs from bubble, and when you would reach for it. Next up, insertion sort. How humans actually sort cards, and it has a best case of linear time. Subscribe and I will see you there.